Okay, so today I'm going to present a joint work with Jens, David, Mohammed, and Ben, focusing on vulnerabilities in systems utilizing zero-knowledge proofs. So, the main incentive for attackers to finding and exploiting vulnerabilities is the prospect of financial gains. So far, systems that utilize zero-knowledge proofs are only a tiny fraction, contain only a tiny fraction of the total value logged in the blockchain ecosystem in general. So, although there have been some pretty severe vulnerabilities in deployed systems, we haven't observed any major attacks so far. And another reason might be because ZKPs are kind of difficult, and until recently, not many people actually worked on them. Two such examples are the ZK's counterfeiting vulnerability and an under-constraint issue in Tornado Cache. So in this talk, we are going to discuss a bit about the impact of ZKP vulnerabilities, layers in which bugs can be introduced, and we're also going to present a taxonomy of common ZKP vulnerabilities, and we'll conclude with a brief discussion about countermeasures and defenses. So to perform the taxonomy, we gathered bug reports for various resources, like the 0xSpark community ZK bug tracker, some blog posts, some auditor reports, and also the bug tracker of major protocols. In total, we have gathered more than 100 bugs, but so far we have only processed 45 bugs. And in the following of this presentation, I'm only going to discuss vulnerabilities that we have actually already studied bug in a real-world project. So, ZKPs have three fundamental properties. First one is soundness. Soundness means that if a statement is false, then no malicious prover can convince an honest verifier that this statement is true. But if there is a vulnerability in the verifier, then maybe the cheating prover can actually convince the buggy verifier that a statement is true when in reality it's false. And the impact of such vulnerabilities could be like, for example, in a project like Tornado Cache, if we have a soundness issue, then maybe an attacker can basically get all the funds out of a pool. The second property is completeness, and completeness means that honest prover can always produce a valid proof for a valid statement. And if we have a vulnerability or a bug in the prover, then maybe that can lead to denial of service attacks. And finally, we have zero knowledge, which means that proofs should not leak information about private information. And again, we can have some sort of attacks at this property. So, to build, implement, and use ZKP application, we have those layers. The base layer is obviously the hardware, the operating system, the runtime. On top of that, we have the proof system, and here we're referring to basically the specification of a proof system or the paper that describes the algorithms, the inputs, and all the details that someone should then implement. And the next layer is ZKP tools and libraries, such as the circumsnark.js toolchain, Hello2, etc., where people can actually write circuits. And these libraries typically use like a highly optimized, low-level field arithmetic and elliptic curve libraries. And on top of that, we have the actual circuits that people write using those frameworks. And the final layer is the ZK application with which users actually interacting. So in this study, we don't focus on hardware and field arithmetics, and we also do not consider like any vulnerabilities that are not ZKP related in the application layer. So we don't care basically about range vulnerabilities. So far, from the 45 bugs we have studied, 27 are in the circuit layer, 11 are in the framework layer, which is still a pretty big number for 45 bugs. And then we have 6 bugs in the ZKP application layer, and these are typically pretty easy to fix. And also, we have studied 2 bugs in the proof system layers, and that could have like severe implications because any implementation that basically implements that proof system may be susceptible to some attacks. Here is our taxonomy. This is already a bit outdated, but as we can see, like most of the bugs are soundness bugs. And this is the main thing in the ZKP space at the moment. And I feel like those kind of bugs will be the target for some attacks in the future. So if we go to the application layer, the first root cause of vulnerability is missing input validation checks. And for example, basically, we can have a solidity contract, and then we forgot some required statement, and that can lead to a completeness or a soundness issue. On the circuit layer, so far we have only studied some sort of under constraint issues. So all those categories basically are under constraint issues, and we have characterized them as logic errors if we cannot include them in any of the more fine-grained categories. And for example, here is an arithmetic overflow in a Hello 2 program, and if we remove the constraint in the second line, then there might be some overflow issue that could lead to a soundness bug. And finally, we have a framework in which there are 2 kinds of bugs. The first one is in the code that is generated from the framework to be used in the application layer. And typically, missing input validation checks are that kind of bugs. And we can have some lower level bugs, such as weak randomness, compiler optimization bugs, etc. And finally, in the proof system, as we already discussed, those bugs can have like really severe implications in all implementations of those proof systems. So what we can do? Obviously, we can do auditing, and auditing is a common practice in the whole blockchain ecosystem, and definitely most of the biggest ZK protocols are doing audits. But before auditing, we should educate ZKP developers and security researchers on ZKPs, vulnerabilities, and security-related issues. So there are already quite a few high-quality sources that people can study and learn more about ZKPs and ZKP security. And we can also develop better tooling. So by better tooling, we mean better DSLs that people can write circuits, which is the main issue in the space at the moment. And those DSLs could eliminate some of the categories of vulnerabilities in the circuit level. There is already some application of formal methods for detecting ZKP vulnerabilities, especially in the circuit level. And as we can see, like from the examples here, most of these tools currently focus on the circuit level and mainly on soundness vulnerabilities. So what are the initial insights of this work? First of all, what we are missing is proof of concept exploits. And we are currently working for all the bugs we have gathered to actually create reproducible proof of concept exploits. And that's important for both developers, but also for tool developers that want good benchmarks for their tooling. Furthermore, we have identified some primary sources of vulnerabilities. And the first one is optimizations across all layers, where we try to optimize some things and then something else breaks. Mismatches in field sizes, some specific peculiarities of DSLs and libraries that are difficult when you start writing circuit in DSL. And also another common mistake is when we reuse a gadget or a component, we forgot to properly constrain the inputs and the outputs of this gadget. Moreover, we have identified some things that we need to improve with regards to tooling. We think that the main tooling that is currently missing is testing frameworks. And that's kind of expected because there are many moving parts at the moment in the space. But as the space becomes more mature, we are expecting more testing frameworks. And another important point is that to detect some particular bugs, you might need to have tooling that can analyze both the circuit level and the application level at the same time. And finally, bugs in lower layers can have catastrophic impact in all the layers above them. So as a future work for this study, we want to process more bugs and proof of concept exploits to our dataset, add missing vulnerabilities from the categories we have in taxonomy, because there are some bugs we haven't still processed, and also we wanted to integrate it with the 0xSpark GitHub bug tracker and update it there. So, in conclusion, do we have to be scared about what the future will be? And the answer, I think, it's both yes and no. Yes, because as more TVL going through ZKP systems, then attackers will have greater incentives to actually focus on ZKP systems. And there are also some difficulties, like the meta model for onboarding developers. It's kind of different from other domains, so that might be an issue. Also, vulnerabilities are complex and hard to detect. And there is also some lacking of better tooling that we need to develop. But we also can be positive because there's already great efforts of developing better DSLs and tooling, and there are already many great researchers and auditing teams and great educational resources that we can use in the space. So that's it, and here are the main resources for this work. Thanks a lot.